Difference amplifier circuit design and use cases. Let's dive right in. Today, we're looking at what's honestly one of the most elegant tools in electronics, the difference amplifier. If you want to know how hardware can literally do math without a single line of code, well, you're going to absolutely love this explainer.
So, let's kick things off with a little puzzle. Picture two containers of water, right? And they're at totally different temperatures. You want to measure the exact temperature difference between them instantly, in real time. Now, dropping a sensor in each container gives you two varying voltages. But how on earth do we isolate just the difference between those two signals?
I mean, sure, you could just grab an Arduino and write a bunch of software to do the subtraction for you. But honestly, that is massive overkill. It's kind of like rolling out a giant bulldozer just to plant a single little flower. It eats up precious power and resources when a much cleaner, simpler solution is sitting right there.
Enter the difference amplifier. By using a basic operational amplifier chip, an op-amp, configured this way, we can subtract those two voltages instantly. There's no code, there's no clock cycles. It is just pure physics doing the heavy lifting and doing the math in real time. It's actually really cool.
Now, before we actually build one, we've got to remember the two golden rules for op-amps in a closed loop. Rule number 1, infinite input resistance. This basically means absolutely no current flows into the input terminals. And rule number 2, the op-amp constantly drives its output to keep the voltages at both of its inputs exactly equal. Keeping these two rules in mind makes analyzing this whole circuit surprisingly simple. And putting it together, it's incredibly easy. Step 1, you just start with your standard op-amp chip. Step 2, run a feedback resistor right from the output back to the inverting input. Step 3, connect a resistor from the non-inverting input straight to ground. And finally, just feed your two signals into both inputs through their own separate resistors. And honestly, that is the whole shebang.
So what you end up with is the classic difference amplifier, also known as a subtractor circuit. Because of the specific way this resistor network limits the current and dictates the voltage drops, the output voltage emerges as a weighted difference between those two input signals.
But here's where it gets really beautiful. If we carefully balance the resistor ratios on both inputs, that weighted difference becomes perfectly equal. The math distills down to an incredibly simple equation. Vout equals V2 minus V1. Just perfectly clean subtraction.
So why does this matter so much? Well, it all comes down to the common mode rejection ratio, or CMRR for short. You see, out in the real world, unwanted electrical noise often infiltrates both inputs equally. But because this amplifier only cares about the difference between the two, it naturally subtracts and completely rejects that shared noise. It's brilliant. Just keep in mind, getting a really high CMRR relies heavily on having super tight tolerances for those resistors.
Now for a real-world application, let's say we add a resistive bridge, sometimes called a Wheatstone bridge, right to the input terminals. Doing this transforms our standard difference amplifier into a highly precise differential voltage comparator. It's basically comparing one input directly against the other with laser precision.
For instance, if you set a fixed voltage reference on one leg of that bridge and then swap out the other leg with something like a light-dependent resistor or a thermistor, the circuit starts reacting linearly to its environment. The output voltage will actually rise or fall super smoothly, tracking even the most minute changes in light or temperature.
And because they're so incredibly robust at filtering out that noise, difference amplifiers are absolutely essential out in the wild. I mean, they are doing the heavy lifting for current and voltage sensing inside solar panel arrays, everyday power banks, DC-to-DC modules, and even complex industrial programmable logic controllers. They are everywhere.
They really are just everywhere, quietly doing math using nothing but raw physical properties. So I'm going to leave you with this question to ponder. Instead of instantly reaching for a microprocessor the next time you're building something, how might you use a simple op-amp chip and just a handful of resistors to let physics do the math in your next DIY project? Think about it.